Here we're going to find the critical point and phase portrait of the given autonomous first-order differential equation and also classify each critical point as stable or attractor, unstable or repeller, and semi-stable. We call the right-hand side of this differential equation f of y, and we need to find the roots of f of y, that we call those roots the critical points. For f of y to be equal to 0, either y has to be equal to 0 or ln of y plus 2 has to be equal to 0. And we know that ln of 1 is equal to 0. That means that y plus 2 has to be equal to negative 1. So these two critical points of y equals 0 and y equals negative 1 will divide the y-axis into three different regions. So the first region will be for the values of y less than minus 1, and we can pick minus 3, and we need to find the sign of f of minus 3, which is minus 3 times ln of minus 3 plus 2, and we know that this is positive. So we can draw an upward arrow in this region. Then the next region is for y between minus 1 and 0, and we can pick the value of minus 0.5, and we need to find the sign of f at point y equals negative 0.5. And this will be negative, and it means that we should draw a downward arrow between 0 and minus 1. And the third region is for the values of y greater than 0, and we can pick y equals 1. So f of 1 is 1 times ln of 1 plus 2, and we know that this is positive. So we need to draw an upward arrow in this region. So the first critical point, which is y equals 0, any values greater than it, it's increasing. And for any values below it, it's decreasing. So everything is moving away from point 0. So we call point 0 a repeller, or we can say that y equals 0 is an unstable critical point. Then for the other critical point, which is y equals negative 1, any values greater than it, it's decreasing. And for any value less than it, the f of y is increasing. So y equals minus 1 is an attractor, or we can say that it's a stable critical point.